All right, today we are diving deep into the architecture of speed. We're talking about particle accelerators, which are some of the most powerful and, surprisingly, most common machines here on Earth.
Okay, so let's just jump right in with a question. What do cancer treatments, food sterilization, and, understanding the entire universe, what could they possibly have in common? I mean, on the surface, they seem like they're from completely different worlds, right?
Well, the answer is they all rely on one of the most powerful scientific tools ever invented, the particle accelerator. These incredible machines are kind of the hidden engines driving progress in fields you would never ever expect. And today, we're going to pull back the curtain and see exactly how they work.
All right, so first things first. Before we get ahead of ourselves, what is a particle accelerator? Let's just break it down, get to the core of it. So, at its heart, a particle accelerator is a machine that does one thing, and it does it really, really well. It takes tiny charged particles, think electrons or protons, and uses powerful electromagnetic fields to get them moving incredibly fast. But it's not just about speed. The real goal is to pump them full of an insane amount of energy.
And when I say fast, I'm not kidding. We're talking about getting these particles up to, get this, over 99.9% of the speed of light. That's it. That's the cosmic speed limit. There's nowhere faster to go. And it's at these insane speeds that, well, the really interesting physics starts to happen. Okay, so we've got the what, but what about the how? I mean, how on earth do you get a tiny particle to go that fast?
Well, probably the easiest way to wrap your head around it is to think of it like this. Imagine a super high-tech racetrack, but for the tiniest cars in the universe.
And on this racetrack, you've basically got two main controls. The electric fields, that's your accelerator pedal. They give the particles these perfectly timed pushes to make them go faster and faster. And the magnetic fields, well, that's your steering wheel. It's what bends the path of the particles, keeping them perfectly on the track, exactly where they need to be.
So this whole race really happens in 4 key stages. First, you need your particles, right? That comes from the particle source. Step 2, the accelerating system kicks in. That's our electric fields doing the pushing. Step 3, all of this happens inside a vacuum tube. And this is super important because it makes sure the particles don't bump into any stray air molecules. And finally, step 4, you have the detector system. Think of it like a super sophisticated high-speed camera at the finish line capturing exactly what happens. Okay, so we've got the basic idea down. Now let's talk about the 2 main ways these things are actually built. So you've really got 2 main flavors. On one hand, you have linear accelerators, or LINACs. These, as the name suggests, shoot particles in a straight line. It's like a single all-out sprint. These are the kinds you'll find in hospitals for radiation therapy. Then you have the circular accelerators, like a synchrotron. Here, particles go around and around in a giant loop, building up more and more energy with every single lap. And of course, the most famous example of this is the Large Hadron Collider. And this really shows you the insane range of scale we're talking about. I mean, you can have a medical LINAC that fits neatly inside a hospital room, using its beam to target cancer cells with incredible precision. And on the other end of the spectrum, you have something like the Large Hadron Collider, with a tunnel that's 27 kilometers long, basically the size of a small city, buried deep under the ground. And this brings me to what might be the most surprising part of this whole story. We hear particle accelerator and we think of mind-bending physics and Nobel Prizes, but their biggest impact? It might be a lot closer to our everyday lives than you think.
I mean, look at this list. The applications are just wild. Yes, of course, they're crucial for fundamental research, like hunting for particles like the Higgs boson, the one that helps explain why things have mass. But they're also absolute workhorses in medicine, used for cancer radiotherapy and then things like X-rays and PET scans. In industry, they sterilize medical tools. For security, they're scanning cargo at airports and ports. Their reach is just massive.
And here is the real kicker. If you look at all the particle accelerators out there in the world, the vast majority are not being used for that high-level fundamental research. Nope. Most of them are the workhorses in our hospitals and factories. They're directly impacting our health, our safety, and the stuff we use every single day.
So that's where we are now. The big question is, where are we going? What's next for this incredible technology? So just to recap, we've got these incredible machines that can be small enough for a hospital room or as big as a city, all designed to whip particles up to nearly the speed of light for everything from pure research to practical, real-world applications.
Looking to the future, the big push is to make these machines smaller, more efficient, but even more powerful. And the goals are huge. We're talking about developing even smarter cancer treatments, designing brand new materials atom by atom, and even getting closer to solving some of the biggest puzzles in the universe, like what exactly is dark matter?
You know, when you boil it all down, it comes back to this one idea. These machines aren't just for scientists in a lab somewhere. They are truly one of the foundational tools of the modern world, shaping our science and our lives in ways we probably don't even realize.
So I'll leave you with this to think about. From unlocking the secrets of the atom to helping us fight cancer, these machines have already completely changed our world. It just makes you wonder, what mysteries will the next generation of them unlock?